In this short video, I will show you how to create this part in Apex as well as setting it up and solve the analysis. Once you have Apex open, you can enter the geometry creation environment through accessing any of these tools. First step is to pick a plane on which to create the part. Let's choose the YX plane and you'll see the origin indicated over here. Once you're in the sketching environment, you'll see that the default settings allow you to select any position on the grid, and by default these entities are 20 millimeters apart. For this example, I would prefer having these entities 10 millimeters apart, and for that I'll simply change the grid spacing from the default 200 millimeters to 100 millimeters. Now I have the option to very easily create the lines 10 millimeters in length. You can very easily create the curve and pick the correct center location, which is 30 millimeters below the origin with a 40 millimeter radius, and the second one with a 20 millimeter radius. So as you can see, very quickly I can create the sketch. I can pick any position or intersection. These options that you have over here allows you to do other things as well, like snapping to extensions, guides, etc. For this case, the default is quite easy. We now simply use the trim tool to trim off all the elements that we don't need. And there we have our first structure, and the moment we exit, you'll see that the full sketches option is on and we have a sketch created. If you see a rough estimation of curves like this, this is very easy to change through the options, going to the tolerances menu, and you can pick a fine resolution. It uses a little bit more of your screen card capabilities, but in general it gives you a good resolution of round edges. Now the next step is to rotate and copy this part into the appropriate position. Remember, we chose this coordinate as the origin of the model, and that's quite useful in this case. I'll enter the transform tool and I'll choose the option to copy the part, and I'll pick the part to be copied. The moment I pick the part, the translation triad highlights, and I can use that to reorientate and translate my part. For this rotation option, I don't want to rotate the part about this location. I would like to rotate it about the origin. For that, I need to unlock the triad. You'll see it changes a slight gray. And now I can define the new origin for this triad at that location, at which point I can now lock it again. And now I'll be able to rotate the copy about that location. To go into the rotation mode, I simply press R for rotate on my keyboard, select the appropriate direction in which I would like to rotate the part, and enter 180 for the number of degrees that it needs to rotate at. And that is all I needed to do to create this geometry in Apex. Now let's proceed setting up the finite element model. The very next step is to create a mesh for our surfaces. We can start by a default mesh of 5 millimeters and see what the quality of the mesh looks like. This doesn't look too bad, so we can use it like that, or maybe use a finer resolution just to check what that does. We can play around with various options and various other parameters to see if this helps us at all. And you can see in this case a map mesh is not suitable, while this mesh option probably gives us a better distribution and element quality. You can actually validate the element quality by hiding the geometry and looking at the element quality index as we have over here, and what we see is that all the elements are good except for one single poor element, but luckily that element is not in an area of stress that we are interested in, So this is in fact a good mesh. After we've meshed, we can now attribute the constraints, and I will do the constraints as follows. I will constrain the bottom edge of this structure to be able to freely move in the X direction, because since we're going to have this part in tension, we know that it will most likely stretch, and it would like to, due to Poisson's effect, become narrower in this direction, so we cannot restrain the X direction. So I'll keep the X direction free for this edge while locking the Y and Z translation so that the part stays in plane, and I might just unlock rotations about Z, although that's unlikely to occur. I'll now zoom in and pick the edge, and that is how I've now selected and made sure that the structure at that edge will not translate in the Y or Z directions, but still be free in the X direction. I do now, however, need to lock the structure as a whole somewhere in the X direction, because otherwise it will be free to move in that way, and that is not allowed for linear static analysis. So for that purpose, I'll simply pick a single node in the middle at that location to make sure that the structure as a whole cannot translate. While I'm busy with this, I've realized now that I've never checked whether or not these meshes were actually connected. To do that, we enter the geometry edit area and hide the finite elements. And what we would like to see is that we indeed have red edges on the free edges, but green or yellow edges on the shared edges. And as you can see in this case, the shared edge is also red, meaning that these meshes will not be connected. And this is highlighted when you enter any of these tools over here, or when you select to have the rendering on over here. So what I'll simply do is enter stitching mode and stitch these two surfaces together. The moment I've done that, you can now see I have a green edge, and the green edge means that I now will have a connected mesh. I can visualize my mesh again and just check that the constraints are still applied. And the one thing that I do see is that there is an exclamation mark, and the reason is that the one constraint that I did apply was now removed due to the remeshing that took place when I stitched those surfaces. So what I can do is to simply reapply this constraint in the appropriate position. Do note, however, that I did not pick the constraint under the list of constraints, but I listed the constraint under the part, and there is a difference. This is in fact a global definition of the constraint, while this is the local part level definition of the constraints, which dictate where the load is applied. When we enter these constraints, we can modify the properties of that constraint, but we cannot reassign the location. To reassign locations of constraints, we need to enter this level of the constraint in the model browser. So that's just a slight difference on how that works. In the assignment, you are required to distribute 1 kilonewton along this edge, meaning that we have to divide it between these 5 elements. That means each element will receive 200 newtons, and because each element has only 2 nodes, it means that each node will receive 100 newtons. But since these nodes are shared between 2 elements, they will each receive 200 newtons. So let's create a force for the end nodes, and I'll give it a name, end nodes, and I'll define the magnitude as 100 newtons, and I just need to reorientate the direction to be in the positive y direction. So I can change my direction vector to be 0, 1, 0 and press enter, and that changes the direction. Now I need to simply pick those 2 points and I have my 100 Newton loads applied.
Now I just need to create the mid-node forces, and for that I need to double up the force magnitude, and the direction stays the same, so I'll simply pick the remaining nodes where I need to apply that force. Right, so now we have our structure constrained on this edge, we have it constrained on that location, and we have our loads applied. To ensure that the load magnitudes are correct, you can double click on any of these nodes. You'll briefly see the arrow highlighting and it will show you the node magnitude. There you will see the other end, the first one on the middle, third one in the middle, and the last one, and the very last one in the middle. If you just expand this window over here. Maybe one additional constraint that we could consider adding to ensure that the structure stays 2D, in other words doesn't move out of the XY plane, is to add one additional constraint. I'll just call it plane XY, and to constrain all the nodes to not move out of the Z plane, we simply select that constraint. That also means we won't allow any rotation about the X or Y axes, and we can now purely select the surfaces, which then applies that particular constraint to all the related nodes. So we can verify that by checking which nodes are indeed constrained when we select or highlight these constraints on the list over here. So that concludes setting up the boundary conditions and constraints. Now we need to set the material. So I'll be creating a material. The material has a specified Young's modulus. We do not need to define the density at this stage, so we simply define the Young's modulus as 69 gigapascals. Our default unit is in megapascals, so I'll just add the additional zeros there and just ensure that I indeed have only 3 zeros, and then finally a Poisson's ratio of 0.33. The material has now been created. Now I simply need to assign it, and I assign it to this body. Once I've assigned the material, to check that I have indeed assigned it correctly or that it has been assigned to the correct parts, I can expand it in the model browser and simply hover my mouse over the material listed, and everything with highlights shows me where the material has been attributed to. The next step is to define the thickness of the plate. So we do this through sections. We'll create the section. I'll just use the default name, and this is a 2 mm thick section that has now been created, and now I'll simply assign it again to this section in exactly the same manner as we have assigned the material. And again we can verify which parts of the model has been assigned with this thickness, and by simply hovering our mouse and seeing what highlights. So that should be all that is needed to set up the model for analysis. To check that it is indeed correct and finished and ready for analysis, we can right click on the part name, or if we had an assembly or a sub-assembly, we could highlight or select those, right click and set the analysis context. The analysis readiness is now checked for this part, and I see there's an exclamation mark over here showing me that something is indeed wrong and I need to correct that. And what it says here is that I have a missing behavior assignment. So what I forgot was to add a behavior for these shell elements, because shell elements can behave differently. Some may have bending, some may not have bending stiffness. So in this case I create a shell behavior, and the default properties are normally the plates that we would use. They have membrane stiffness, they have bending, and they allow transverse shear, and these default values are fine as they are, so we only need to assign it as well to the spot. And the moment we do that, we now see that our red exclamation mark has been replaced by a green check mark, and it tells us that there is no offenses identified. This means that our analysis is ready to run, and as you can see we have different simulation types, but at this stage we're only going to run a static analysis, so I can simply skip to step 3, which is to run the analysis, because I won't be creating any different sets of scenarios in step 2, so I can just skip that. As you can see, the analysis is now complete, and now we can look at the results in the post-processor. The first thing that we see in the post-processing is the deformed shape of our structure, and we can add a fringe of the appropriate result, which in this case is the von Mises stress result. There are other components that we can show as well, or we can switch to translation to actually see translation values. Now the interesting thing here is that the default deformation is exaggerated, but only exaggerated when the actual displacement is very small. If the actual displacement was very large, our deformed shape in the displacement mode would have actually been reduced as to show it not to be exaggerated, but actually less than the actual deformation. So it's really important to also switch to true scaling to make sure that we see a one-on-one deformation. So switching this on and off, we can see that the actual deformation is ever so slightly, and this is really important to check, because under some cases it might be that the true scaling is much higher, which would invalidate the results for a linear static analysis, and in such a case it might not be as evident when your default displacement setting is set to relative, because it would actually reduce the actual displacement to show a relative scaling and not a true scaling. So that is just useful for those purposes. So you can also animate the results, which now clearly shows us the behavior of this plate. And what is actually nice to check is how our boundary conditions make this structure react. So we can clearly see all the nodes on this edge are allowed to move in the X direction, but the structure as a whole do not move in the X direction because we've locked that single node. So because of this node's X constraint, our structure isn't unstable, and you can actually see how this portion of the structure actually displaces in the opposite direction from those ones, even though our loads are applied vertically. We also have the option to manipulate what is displayed in the post-processor tab over here, where we also, if we had multiple parts, could visualize selective parts. And this concludes this tutorial on how to complete this question using Apex.